Okay, we're going to look now at the life cycle of a star. There's a really good video available on YouTube. I think it's called, it's about star death and creation of the universe, creation of the elements. It's done by Professor Brian Cox, and the BBC series was called Wonders of the Universe. So if you Google star death and creation of the elements with Brian Cox in it, you should be able to get it. Right, what you need to know about a star life cycle is there's actually three main routes, okay? So all stars start off with hydrogen. And then at that point, it goes down two branches. The branch on the left is where our star is at the moment, and basically our star, the sun, will make elements up to iron. Going back to the start again, if you start with hydrogen, if you've got a star that's 20 times bigger than our sun, 20 times bigger plus, 20, 30, 40, 100, maybe 2,000 times bigger the size of our sun, it will go the other way to the right. And then at that point, it will form elements that are heavier than iron, so things like plutonium, uranium, gold, lead, all of these things are heavier than iron, all these elements are, and that goes down that chain there. So that's the general shape of the life cycle of a star. And we'll go into a bit more detail now. Right, so a protostar is basically a hydrogen and helium cloud, and all these hydrogen atoms and helium atoms are attracted to each other by gravity, but at this point here, there is no nuclear fusion taking place, so that it's not giving out any energy or any light or any heat, and that's the protostar. Now, gravity begins to pull things further and further in, until eventually gravity pulls it so hard, and the particles are moving so quickly that hydrogen atoms then begin to fuse together. Then at that point, you release energy. So that's when fusion happens, and that is known as the main sequence star. So the main sequence star gives out energy, the protostar does not give out energy. So in the main sequence star, you've got hydrogen and hydrogen being combined together to make helium, and that nuclear fusion process takes place. The star stays more or less the same size because gravity is pulling it in, as shown by the red arrows, but at the same time so much heat is generated that it pushes the particles out. It's called thermal pressure, and those two forces, one pushing out, another one pushing in, it keeps the star in a constant shape. And as I said before, hydrogen has been turned to helium. After a while, helium begins to be fused as well. So let's look as to what happens to stars the same size as our sun. Well, once all the hydrogen has been turned to helium, it then does something called helium fusion. Now at this point, it releases a huge amount of energy, so much energy that the star expands enormously and forms a red giant. And in this section here, in the middle of the red giant, in the core of the red giant, there's temperatures of around 100 million degrees C, much hotter than the 15 million degrees C of the main sequence star. And this temperature is hot enough to allow helium to combine to make heavy elements such as carbon, such as oxygen, all the way up to iron. And then at that point, once it's reached iron, the star will then collapse and then explode, and what's left behind is the core of a red giant. And that core is a white dwarf, a very, very dense, tiny star. And as it cools down, it turns into yellow dwarf, into an orange dwarf, red dwarf, brown dwarf, and eventually a black dwarf. So these are very, very small stars, but very, very dense. Okay, so that's what will happen to our star. It takes about 15 billion years. If you've got a star that is much, much heavier, much more massive than our sun, and I said earlier about 20 to 100 or maybe 1,000 times bigger than our sun, one of these two things will happen. Once it's used up its hydrogen and it's formed helium, it will then form a red supergiant. Now this is a massive, massive star, and much bigger than the red giant. And this red supergiant will again go through, produce all the various elements up until iron, and then when it's reached iron, at that point it collapses, and as it collapses in on itself, when it gets as small as it possibly can, it stops with a shuddering jolt, and this sudden jolt causes it then to explode into the biggest explosion in a galaxy known as a supernova. Okay, and that supernova has enough energy in it to cause iron to fuse together and produce heavier elements like lead, like gold, like platinum, like uranium. All of those have been made inside supernovas. So if you've got any gold or any iron or any gold or any lead at home, they were made in supernovas. It's really interesting and cool to know that. Right, so at this point, one or two things can happen. If the star is, say, 20 to 30 times the size of our star, it will form a neutron star. And the neutron star is basically a star made up exclusively of neutrons. The neutrons are packed next to each other. They're sort of touching each other. And it is so dense that a teaspoonful of a neutron star will weigh about 100 million tons. If your star is much bigger than that, over 30 times the mass of our sun, it will form a black hole. And at this point, what happens is the gravitational force is so big that even the neutrons collapse in on themselves, and at that point you form a black hole, and nothing, not even light, can escape. And that there is the life cycle of a star. It's a very, very common exam question. Just make sure you can remember the exact order of each of the stars there. The keywords I've underlined, if you notice. The keywords are underlined in red. Red giant, white dwarf, black dwarf, neutron star, black hole, supernova, supergiant, protostar. And just make sure you know that it's hydrogen to helium, and then it ends up as iron. And then on the other side, to produce elements heavier than iron, you have to have a supernova taking place.